I'm Professor Alex Girard from Sherbrooke University. Today I'm going to talk about extra robotic limbs. I'm going to give a brief research overview of what the technical challenge we are trying to address in my laboratory. And also where the focus would be actuator. What are the big challenges in terms of motor and other way to actuate those robots? So first, let's talk with looking at a little bit what science fiction is showing us. So we have a lot of inspiration from science fiction works, but in terms of what engineers are building today, we are a lot behind what we see in the movie. So I think in some sense, we need to work harder to catch up with the dream. So before discussing actuators challenge right away, I'd like to first discuss a big overview of what we are trying to do, what are the many challenges we are trying to address, and how actuation fits into that big picture. So first, what are we trying to do with those wearable robotic system? So one big challenge we are trying to address is that traditional automation with the industrial robot is not a very good option in many sector, especially sector where you need to build like a building, for instance, or ship any big assembly where you have a low rate of production. They don't meet the requirement so that using traditional automation is a good idea, basically. And in those fields, it's still mostly manual labor that is used for building those big assembly, either a building or an airplane, ships. And there's a lot of issue. The workforce is aging, and there's a lot of injury in those fields. So how can we use robot to help those industrial sector? Is basically what we are trying to do. And an alternative to full automation, which in those sector I would say would be quite far away, is I'll be moving this. I think it will be better. Yeah. So one of the big challenges we are trying to address is this disappearing? Oh, all right. Sorry. Uh, so one of the ideas is instead of trying to fully automate those fields, let's try to augment human worker. We don't want to replace them. We want to improve them basically. And there's good kind of the idea is basically humans are very good at some task, and maybe we can leverage the good ability of the human and also the good side of a robotic system and to create a good system where both human and robot can help us in those sectors. And this is where wearable robots are coming in. Two big idea is that accessibility to manufacturing site is a challenge. So humans are very good at navigation in complex environments. So maybe we can use human to go where we need to do some manufacturing operation, for instance, instead of having a complex robotic system just to navigate a complex manufacturing site. And the other interesting aspect is in those sector, uh, all manufacturing operation are not like 100 times a day doing exactly the same thing. It's always things a little bit different because it's a big piece that we are building, let's say for a house or ships, and it's always a little bit different. It's not always the same all manufacturing operations. So having a worker on site managing this kind of uncertainties about every single operation would be also a good plus for the system. So today I'm gonna mostly focus about the robot that we are building for human augmentation. It's not it's not the only field that could benefit from such system. There's also rehabilitation, elderly assistance, prosthetic. Uh, I'm gonna focus on this, but it doesn't mean that the technology we are developing will not be useful for all those other area. In fact, many of the technical challenge are similar for also exoskeleton, prosthetic, any kind of wearable robotic system. They share a lot of the challenges. So let's now look a little bit at what people have been trying to build and use in terms of wearable robotic system. So the one that most people uh, know are exoskeleton. So a few people have been trying to work on exoskeleton, and there's I would say one axis in terms of goal, what people are trying to do. So some people are building very lightweight exoskeleton where the goal is metabolic cost. So basically, they want to produce very small force just for a human to be able to carry a bigger load without for a longer distance without too much fatigue, for instance. On the other hand, the big exoskeleton, the goal is different. It's trying to increase this human strength, basically. There's also an interesting passive device that people have been building, and probably those, I think those will be the first type of wearables, not really robotic system for say. I don't think we can call them robot, but I think those devices is going to be the first thing on the market, and maybe those thing with a little bit actuation is going to be the first robotic system we can really penetrate the market for the kind of a low-hanging fruit in some sense. And so interestingly, those devices they have different goal too, but it's mostly strength and fatigue that they can help. So for instance, the device here in the center, the idea is to compensate for the gravity so that you can manipulate heavy object more easily. And also, you can help with fatigue by basically supporting the human body and posture where you easily fatigue yourself. And the focus on the talk here would be about extra limb, supernumerary limbs. So third arm or third leg, those type of things, or also even finger, for instance, here. So today I'm working on mostly arms and extra leg in my laboratory here in Sherbrooke University. But in the next few slides, I'm gonna discuss a kind of overview, also including a few of the experiments done at MIT, where I spent 4 years in Professor Asada laboratory. So I'm gonna try to take a step back to discuss kind of the global technical challenge. And then at the end, I'm going to go back to in more detail what I'm currently doing in more detail. So first, why? I'm sorry, there's again the problem with this here. It's gonna disappear. Ah, there you go. So where was I? Yes. So why extra limb and not just building better exoskeleton? It's a first a question that comes to mind when you people see what we are trying to do. So there's multiple advantage for extra limb. The first one is simple, is that the kinematic can be easier if you are not trying to follow the human body. So it's just a mechanical design advantage, basically. The human body, especially the joint, are highly complex, and trying to match them, the kinematic of the human body is hard. So for instance, here, if your goal is basically uh, provide a force here at the payload and transfer this force to the hips, for instance, of the user, then going straight to the goal with this parallel structure, maybe it's a better idea than trying to follow the complex kinematic of the shoulder, for instance. Also for here, this is one of the third leg we have been exploring in my lab. It's also, the idea here is that if you want to produce a force to support the user here at the lips, at the hips, then here with a very simple 2 degree of freedom wearable cane, we can go from the hips to the ground with a very simple mechanical design. And it would be much more complex to try to follow exactly the knee and all the legs of a human, basically. And so this is kind of a practical advantage. And the other interesting thing is that if you're not following exactly the human body, then you can also try to do tasks in parallel, like a coworker. So you don't have to just add force to the human. You can also do something different. So it's kind of opening many new possibility compared to just exoskeleton. So now let's discuss the big technical challenge that we are trying to work on in the field. So one of the biggest technical challenge, and many people are involved with that, is the human-machine interface. I like to separate the different approach in two big families. So one is direct, where you basically have some observation signal. They can come from, it's mostly either EMG, IMUs, strain gauge, or encoder, and you connect directly those signal to a controller of the wearable robotic system. The indirect approach is where you try to put some intelligence in between. So from observation, maybe you want to infer human intent, and then knowing the human intent, then you try to do something smart to help the human, is what I call indirect. So there's advantage of both scheme, but personally, I think I think there's some interest in keeping this very simple with a direct approach. And for a wearable robotic system, it's relevant to for user to feel empowered by the device. And one of the things we've learned is that it's a maybe we should try not to build wearable robot, but more like advanced wearable tools where the human is always in direct control and use this tool like an extension of his body instead of trying to fully automate part of the process. So, but this is really a research topic that we are many people are working on to explore. So just a few examples of different approach. So one of the things that was done at MIT, and this one I was a human tester in this experiment, was trying to connect directly EMG to the simple robotic system. And it was shown that you can do that for a very simple task, and the human can learn how to kind of use new communication channel where there's no intelligence in the channel at all. Uh, Another thing we are doing that I would call direct approach is with IMUs. And for exoskeleton or wearable cane, we are using IMUs and to monitor the legs, and then we can make almost direct mapping from leg motion to assistance for exoskeleton or motion of a wearable leg that I will be showing later on. So for cyclic motion like walking, it's a little bit easier than any kind of motion in general. Also with IMUs, at MIT, an interesting research was done trying to infer human intent. So the idea is that you recognize some motion is the human trying to do some task, and then you automate the robot to do something useful for this task. And the same thing was done with also IMUs or just strain gauge here in the term of monitoring what the human is doing and have the robotic system adjusting to a kind of human intent here, monitor from the strain gauge. So this is a really hard challenge, the communication channel, uh, especially for extra limb. And the research, I would say, is still very low TRL, especially for multi-degree of freedom system. We we are still trying to get basic tasks to work, and if you need to control many degree of freedom, it's really hard. For exoskeleton or walking assistance, we are starting though to get some good control working, but it is still a hard research problem that that a lot of researchers are working on. Another big technical challenge, changing from the human-machine interface, is uh, another problem of having the human in the loop is the human motion can disturbate what a robot is trying to do, a wearable robot. So here, this fake video really illustrates well one of the challenge. Let's say you have a third arm, robotic third arm, and you want to do something like painting the wall or holding something. You probably want to control the robotic arm with respect to the room, basically the inertial frame. Uh, and if the base is attached on the human, then the base is probably having dancing is an extreme case, but even if the human is trying not to move, there's always a small motion of the human. So how to do good control of the effector with a moving base that you don't fully control is a challenge. First, it's a sensing challenge because sorry, if you want to position this with respect to the room, you need to know where you are with respect to the room. So this involves IMUs and vision to try to figure for the robot where it is with respect to the room. And a lot of people have worked on sensor fusion, IMU plus vision with very good result. But in this case, what is normally kind of simultaneous localization and mapping that has been developed is uh, is not to put the estimation of the position in really high bandwidth closed loop control, which what we would need here to compensate for human motion. So how to do sensor fusion really fast to do good human motion compensation is a challenge. Or instead of trying to compensate for human motion actively, maybe if the actuator are somehow compliant, you don't need to actively compensate for all the motion of the human. For instance, the what we're trying to do here is basically like a car suspension. We want to provide a force here, compensating for gravity, and we don't want any motion from the human to be transferred to the point here. So like a car where you want to hold the car in the air, but you don't want road motion to be transferred fully to the car. So maybe by instead using some kind of compliant actuator that can reject kind of high frequency motion of the uh, the human user here, it would help. So trying to use a good hardware instead of having just fast sensing and a actuator. Oh, and just a quick video. You probably have already seen this, but it's always a good motivation to see that what we are trying to do, well, nature has already done a pretty good job. So this chicken here has really good inertial control of his head, despite the disturbance of the base. So yeah, we need to figure out a way to have actuator and control to stabilize something with a moving base. It's another challenge for a wearable robotic system. So this is an experiment at MIT that was done a few years ago trying to address this. And you see, it's not only trying to hold something in the air that can be representing a task, but sometimes you might want to control the force that the effector is applying despite motion of the base, which would be the human in this case. And this is illustrating another challenges in terms of actuator where we are going next is the speed of the actuator also can be a problem because you see that if you want to sustain a force here to hold something while the human is using his hand to do something else in parallel, for instance, which is one of the big use case for wearable extra arm. Well, the robot needs to have to be fast enough to move at least as quickly as the human, because if the robot is not fast enough to follow the human moving back, then this will follow directly the human motion and the force will drop to zero and the part will fall. So speed is also important when considering a dynamic task where the human is moving and you need to compensate for it. So here we are coming to this actuator challenge. So with the actuator we currently have, we need to pick 2 out of 3 of those things. So usually robotic system, we have a gear motor. So our system are okay in terms of torque and and weight, but however, if you use a highly gear reduction ratio, you won't have any speed. The robot will be quite slow. On the other hand, if you remove the gearbox, then you can be fast and lightweight with a small motor, but you won't be able to do much because you won't have any payload capability. The other option would be a big motor without gearbox, so a direct drive motor. You can be strong and fast, but the motor would need to be very, very big to have any kind of good payload capability. So this is a challenge in many applications, but it's even more challenging for wearable robotic system. And I'd like to illustrate this with this graphic where we have 2 axes. Here is torque density, so basically force divided by mass. And on the other axis is speed. So let's say what I was discussing earlier is require velocity to compensate for human motion. So if your actuator is too slow, then you won't be able to move as quickly as a human, and it's kind of hard to coordinate with a human for any a little bit dynamic task if you cannot move as quickly as the human. So this kind of a hard threshold here in terms of velocity. And on the other hand, the robot needs to be as lightweight as possible because a heavy robot is kind of burdening a user. And torque is necessary because well, maybe some tasks don't need much torque, but if you want to give a hand to a human and have some kind of a payload capability, then having some acceptable torque density would put you in a situation where it's hard to have both. If you have a big reduction ratio, you will be here. And if you decrease the reduction ratio, then you go here. But we don't have good technology to be directly here. And one of personal frustration with science fiction is that if one thing is really unrealistic about those system here is actuator is one point where it's really unrealistic. So and so when we are trying to build something that do some work here, a wearable robotic system, I think actuation is one of the big bottleneck to do something really useful. So let's take one of the inspiration for the field, Dr. Octopus, and do just a very simplified case study. So let's say we want to do some industrial work and we have this big gripper and a gripper with the payload. Let's say it's 10 kilogram. We want to be able to hold here at 2 meter away from the human here. This would be about 200 Newton meter static load. And um, let's take a state-of-the-art Kinova actuator. So Kinova, you probably know those collaborative robotic arm they are selling for to a lot of research lab. It's one of the very lightweight robotic arm. So they have those nice actuator. They do 12 Newton meter for zero point 0.6 kilogram. So if we extrapolate this, just simplifying linearly, we would get about, for this payload, a 10 kilogram actuator to be able to sustain the static load here. And this is only one joint. So especially for a trunk like this, you would need many, many degree of freedom, many actuator on the many joints. And adding weight on the actuator here you would need to increase the payload capability of the one actuator on the other joint behind, etc., etc. So you would end up with something really unrealistic in terms of actuator weight, what the actuator would weigh. So if we continue with Dr. Octopus, something that would be even more critical in terms of actuator is any type of trunk-like robotic system like this, because you need basically many degree of freedom where you need to apply some torque to move the robot around, and you would be disappointed if you look at real life trunk-like robot in terms of payload capability. Basically, they even have a problem of sustaining their own weight in most situations. So basically, actuators are big bottleneck, especially if you're trying to build a real life Dr. Octopus. The actuators are critical in many applications, but I think for a wearable robot, it's one of the places where they are highly critical. So it's pushing us to develop new technology in this field. And today I'm going to share one approach we are developing and trying to build better robot in terms of actuator technology. So I would like to be able to tell you that I have some magical actuator solution that I can put here in the top right corner of this diagram I was discussing earlier. But until we maybe have some super magnet at the room temperature in the motor or something really game changing like that, it's really hard to avoid this limitation. So we need to be smart about this and trying to kind of go around the problem in some sense. So here are two interesting solutions to explore. The first one is variable transmission, where the idea is basically like in a car transmission, let's shift gear, change the gear ratio. When we want some force, let's use a high gear, and when we want speed, let's use a low gear. So I think Professor Asada is discussing this in the workshop. So today I'm going to focus on another approach that could in fact be combined with this. But the idea is simply all mass is not equal for wearable robotic system. So let's put the heavy part away from the joint as much as we can. So the technology we are working with in many of our prototype is basically adding a hydraulic transmission. So at the joint itself for the wearable robot, there's only slave piston, so we can keep the arm very lightweight. And we put the motor, the gearbox, and all the heavy stuff in what we call power unit that we put, for instance, at the bottom of the backpack where the mass is less critical. And this is helping because for a human, having the mass closer to the CG is much better than mass away from the CG. So it's kind of helping. And also in terms of the performance of the arm itself, it's helping a lot because if there's a very low inertia at the joint of the robotic system, it's helping to go faster to compensate for human motion, for instance. And it's also helping to implement some compliant motion control or force control to having less inertia on the robotic system, which is always good when you have a robotic system interacting with a human. So to keep another critical aspect to wearable robot is the, because it's interacting with the human, we need to be able to control the force that the system is applying, and in order to do that, the actuator need to be transparent. So it need to be low friction, and in order to do that, what we use is a MR clutch in the system to control the transmitted torque, and the piston we are using here are with the rolling diaphragm to minimize the friction in the system. So mechanically, we have slave piston, hydraulic line, master piston. Both piston have a rolling diaphragm to have low friction. And then there's a very small cable in the system just to transmit from linear motion to rotary motion of the clutch. And we can have one gear motor providing motion to many clutch for many different piston. So we can also save on the weight by having a single motor providing power to multiple joint in the system. So here is a demonstration of one of the prototype we did build with 3 degree of freedom. This one is designed for industrial applications, so it's designed for a big payload up to a couple of kilogram. And the power unit for this one is not where by the user. It's on the ground next to the user here. So the challenge we were tackling with this is trying to have a robot that can hold up to I think 5 kilogram at the tips here, while still be fast enough to compensate for human motion and lightweight enough so it's not burdening too much the user. So why are we using hydraulic transmission and not pneumatic or cable, for instance, to transmit the power? Well, cable are also interesting, but mostly if you don't want to put the power unit too far away from the joint, that can work. But because it's quite compact, you can have low friction. It's a good force density. But the issue is with the mechanical design. All the pulley for the cable routing can be complex if you want to go far away from the joint and there's many moving parts between the power unit and the joint. It's the complexity is increasing very quickly. For hydraulic and pneumatic, it's really interesting to be highly modular, to be very so that the arm design can be really independent from the power transmission. Um, The big difference between pneumatic and hydraulic is the hair is compliant, so it limits the bandwidth. It's harder to do precise position control with a pneumatic transmission, while for hydraulics, it's much there's less compliance, but there's more inertia. But we haven't found the inertia to be an issue for, well, it could be an issue if you have very long hydraulic line, but for a few meter, it's not a big problem. And in both cases, with hydraulic and pneumatic, if you want low friction, you must use rolling diaphragm in the piston, and this create a limitation in terms of a pressure, kind of a trade-off, friction or uh, force density for those type of transmission. And also for fluidic transmission, the interesting thing is that not only you can put the power unit maybe in a backpack very easily, but you can also explore other configuration where the power unit is maybe rolling on the ground or even in a central system. And I like to think of this like a kind of vacuum cleaner system with different configuration. You have industrial system where you could have the power coming from the wall or some heavy unit rolling on the side. But if you want to have an autonomous system, then you can have a smaller design with a backpack unit. So you could have custom size system for depending on if you have a heavy payload in the industrial setting or for a small task in a not structure environment. And the one we did design here is mostly for A or B here because it's quite designed for a heavy payload up to 1.5 kilowatts of power per joint, but it's a little bit heavy though in terms of design. So here, this is just showing we did some research also on improving force control despite a moving base, which is one of the basic tasks for extra arm is holding something. So basically providing a force while the user is doing something else. So if the user is doing something else, his hips are going to move a little bit for sure. So can we maintain good force control despite motion of the human here? So we did some experiment to improve control of the force at the effector here, despite the moving base. So here we, due to the type of system we use, we were able to add pressure feedback from the cylinder to improve the force control. And we were able to have a system where you can have very good force control here despite relative motion of the base and the effector, even if the system is not aware of the motion of the base. Another point is the system we are using is highly transparent. So the current in the clutch is almost directly proportional to the effective torque at the joint. So it's very easy to implement impedance control or force control, which is very important since this robot is interacting with the human. We also use the same technology for legs, extra legs. So here it's a kind of a robotic cane where we use it to support the user while walking. So, so the cane here is pushing on the ground to provide some force at the hips during the gait motion. So in terms of challenges here, it's also one situation where you need the actuator to be fast. So during the swing phase, the leg needs to move at like 5 meters per second in the range of this. While on the ground during the support phase, you need to apply very large force. So, like we were saying, this is wearable, so it needs to be lightweight. So it's kind of a fast, strong, and lightweight. Really hard to do for an actuator. This would be, in fact, an interesting situation to use variable transmission because the the speed and the force you don't need both at the same times. It's in a sequence. But also here it's very advantageous to have remotely located the actuation unit because it helps minimize the inertia on the leg itself, which is also very good in this situation because the impacts with the ground can create impulse force that destabilize the user. So if you have very low inertia moving part, it's much better. And in terms of a human-machine interface here, we're using high MUs with a direct approach, basically having a mapping between angle and velocity of the legs and a set point for the robotic cane controller. And we were able to explore a few variation of where to put the robotic cane in the human gait at a different phase and a different harmonic even though. So here on the right, you see the leg is going twice per cycle on the ground compared to here, it's only one time per cycle. So if you're interested in this cyborg gate, this is a topic of the paper we have at IROS this year. So to conclude, wearable robotic system have a lot of potential for helping either worker, elderly, uh, but many big technical challenge to solve between we have a really useful product. So it's a long way to go, but in, in, in terms of for us researcher, challenges are opportunities to explore. So the big one are human machine interface, control scheme addressing the human in the loop, and lightweight hardware, I think, are one of the biggest challenge in the field. So I'd like to thank all the students from Sherbrooke University. Those are the students that worked on the wearable robotic system using a hydraulic transmission line. And I also like to thank the sponsor of my research. And yeah, that's it. Thank you.